Okay, well, let me first of all start out by thanking the organizers for inviting me to be here, Pierre and Stefan and the other organizers. I think it's really a good mix between Jonathan and John and I, because we'll cover complementary topics. We can also, we didn't coordinate ahead of time, but we have all week, so we can coordinate as the week goes on and hopefully fill in gaps that might be missing. Now, my task in this trio is to try to talk about planetary evolution. And so what I'm going to do is spend the first part of my talks talking mostly about the Earth and how the Earth evolves, mostly from a climate standpoint, but also from an oxygen standpoint, because the rise of oxygen is arguably the most important thing that has happened in terms of affecting biological evolution, and especially the origin of complex life would be very difficult if we didn't have an oxygen-rich atmosphere. So I'll talk about planetary climates, I'll talk about the rise of oxygen on Earth, and then I'll talk about the Venus-Earth-Mars problem. Why did Venus get too hot and lose its water? Why did Mars not remain habitable even though it was warm, apparently early in its history? And then this will lead up to the question of, is the Earth rare in the universe, which Jonathan has already touched about from a different standpoint, asking the question, is complex life rare in the universe? Now, I want to put in a plug for my book, which you already heard about, but this is a book called How to Find a Habitable Planet, which came out just last year. The title is ripped off from another book by Wally Broker, Wally is a geochemist at Lamont Doherty University. He wrote a very nice little book about 20 or 25 years ago called How to Build a Habitable Planet. And I decided it was time to update this, where many of you in the room are involved in the search for planets out there. And so that's the next task that we want to do. I think there are some copies available, but I'll pass this one around in case people want to look at it. The book is written at an introductory level, but it has references in it. So I actually wrote it a lot for astronomers who are very smart, know all sorts of things about physics and the universe, but a lot of them haven't studied planets, and in particular, they haven't read the planetary science literature. So there's a lot of references in there. The book was written partly in response to this book that I mentioned in my comment by Don Brownlee and Peter Ward at the University of Washington. They wrote a book called Rare Earth, and their hypothesis in there is exactly what Jonathan went through at the end of his talk, that complex life, including intelligent life, is very rare. And I'm more of an optimist. I should say, starting out, just to introduce myself, I've been at Penn State now for over 20 years, but before that, I was out at NASA Ames Research Center in the San Francisco Bay Area, and I worked with Jim Pollack. Most of you probably didn't know Jim, but he was Carl Sagan's first graduate student. And Sagan, of course, was an optimist on finding life out there, and Jim continued that tradition, and I'm sort of continuing that tradition after Jim. So you'll hear a more optimistic viewpoint from me as the week wears on. All right, so what I want to do is start out with a lecture that's actually very basic, and I'll apologize. The first part of this will be review for many of you, but I want to talk about planetary climates on Earth. So I'm going to talk very quickly about black body radiation and planetary radiation balance, energy balance. I'll mention the greenhouse effect and talk about it in very simple terms, and then if I have time, we'll get to the interesting part, which is modern day global warming, which of course is not simple, and there's lots of debate as to what's going on and what we should do about it. So let me begin with the simple parts here. The Earth is heated by light from the sun. 50% of the sunlight is in the visible region, 40% is in the near infrared, and 10% in the UV below about 400 nanometers. The sun's light is not all absorbed. Here's a picture that shows the solar spectrum at the top of the atmosphere. This area that's colored in is the amount of energy that actually reaches the Earth's surface, and it's about 50% of the total, as Jonathan already mentioned. Only about 30% of the sun's energy is reflected, though. The other 20% is absorbed in the atmosphere, mostly out in the near-infrared here. And these are these near-infrared bands that many of you are, those who are ground-based observers are familiar with this because you're always trying to look in the windows between the absorption bands of water and CO2. From a climate standpoint, we're interested in the absorption bands because that sunlight is absorbed within the atmosphere, and that's part of what heats the Earth. So the Earth and the Sun are both, to first approximations, black bodies. The Planck function describes the energy distribution. There's two important laws that you can get out of that, of course, which we teach even in introductory courses. Stefan-Boltzmann law. Flux is sigma t to the fourth, which gives you the total energy under the curve, and Wien's law, which gives you lambda max is about 3,000 microns over the temperature, and that gives you the peak energy distribution. So if we take the sun at 6,000 Kelvin and the Earth at about 300 Kelvin, you can then use Stefan-Boltzmann law and Wien's law to get the general characteristics of their radiation. The sun's radiation peaks at about half a micron or 500 nanometers, which of course is just in the middle of the visible. And I always ask my questions, my students in my introductory class, where is 0.5 microns in the visible spectrum? Turns out it's in the green. And then I asked them, but the sun doesn't appear green. Why is that? Well, you all probably know the sun is white. If you look at it from space, it's yellow looking at it from the surface of the Earth. And that's because the blue light has been Rayleigh scattered out of the beam. And so color, and yellow is the complementary color to blue. So color is actually pretty complicated, in spite of the fact that Wien's law is very simple. For the Earth, of course, the temperature is 300 K, so lambda max is out there at 10 microns. It's in the thermal infrared. And as Jonathan just mentioned, I like this point about the entropy difference between the sun and the Earth, using that as to drive a free energy gradient that is important for life. And probably John will talk about free energy in his talks. Okay, so once you know just Wien's law and the Stefan-Boltzmann law, you can then do a very simple model, the very simplest model of energy balance on the Earth, and this leads up to how we define the greenhouse effect. So again, in just very simple energy balance, the Earth always has to be roughly in energy balance. The amount of energy coming in has to equal the amount of energy emitted. Of course, that's not absolutely true, because if it were, we wouldn't have global warming. And so right now, the Earth is absorbing a tiny amount more energy than it's emitting, and that we think is leading to global warming. But the imbalance is really very minor, and so again, to a first approximation, you can just assume that what comes in must go out. How do we parameterize the energy going out? Well, the simple way to do it is to assume that the Earth is a black body, and then we're going to derive a temperature, which actually most of you already know this calculation. If we call T sub E the effective radiating temperature, we treat the Earth as a black body, then the emitted energy is sigma Te to the fourth times the surface area, 4 pi times the radius of the Earth squared. That gives us the outgoing energy. The incoming energy, we just take the solar flux at Earth's orbit, which we'll call S0, and that hits the Earth. It hits over an effective surface area, effective area of pi r squared. It's not 2 pi r squared. My introductory students always get confused about that because it's half the sphere, but you have to take the angles into account. So the energy that hits the Earth is the solar flux times pi r squared. Some fraction of that, which we call the albedo, is reflected back to space, so that the energy absorbed is actually S0 times pi r squared times 1 minus the albedo. The albedo, as I said already, is about 0.3. And that's coming almost entirely from clouds. About 0.25 of that 0.3 is from clouds. I'm going to come back to clouds from time to time because we know a lot about climate, but we don't understand clouds. And so that's actually why climate is not a solved problem and why people still argue about things like global warming. All right, well then it's a simple calculation. You just, to do the energy balance, you set the energy in equal to the energy out. S0 pi Re squared times 1 minus the albedo is sigma t to e to the fourth times 4 pi Re squared. And all the pi's and Re's cancel. And you get what we call the planetary energy balance equation. Sigma t e to the fourth is S0 over 4 times 1 minus the albedo. So how many people have seen that before somewhere? Right? Most of you have. That's you can talk about climate, everything else is sort of subsidiary to that. That's the basic equation for the energy balance. The surface temperature, though, is warmer than the effective radiating temperature. And you can demonstrate that very easily by evaluating the effective radiating temperature. The solar constant at Earth's orbit is about 1370 watts per meter squared. The albedo is 0.3, and you put in the Stefan-Boltzmann constant. Solve for T sub E, and you get 255 Kelvin, which is minus 18 Celsius, and it's about 0 degrees Fahrenheit. That is a lot colder than the Earth's surface, right? So the Earth's surface is, we do this from observations. The meteorologists are actually very good about that because they're all interested in calculating the average Earth surface temperature very accurately so that we can tell if it's warming up or not. And so we know that the average surface temperature is about 15 degrees Celsius or 59 degrees Fahrenheit. And I always explain to my introductory students that that means that the Earth is really a nice place to live. 59 degrees Fahrenheit is also the average annual temperature in San Francisco. So where we used to live in the Bay Area for 7 years, and it was pleasant out there. So the Earth is a pleasant place for life, and it's pleasant because of the greenhouse effect. And this is, of course, the other lesson that I have to start out with my Earth 2 students, because they hear about the greenhouse effect as a bad thing because it's increasing right now, but the greenhouse effect, as we all know, is a very good thing because without it the Earth would be quite frozen, right? So the greenhouse effect, the way I like to define it, is just the difference between the surface temperature that you observe and the effective radiating temperature that you calculate from energy balance, and it's about 33 degrees Celsius today, which is 59 degrees Fahrenheit. It's the difference between the very cold and the temperature in San Francisco. So this slide just says in words what I just went through. The Earth is warmed. The greenhouse effect is just the absorption and re-emission of outgoing infrared energy by the atmosphere. Now there's a retired meteorologist at Penn State named Craig Boren who always used to get infuriated when he would hear people say that these greenhouse gases in the atmosphere trap the outgoing infrared radiation. And that's not true, right? That radiation does get out. You can't trap the radiation entirely, but so the atmosphere absorbs it and re-radiates it, some of it going down and some of it going up. And so the correct way to explain it is that the atmospheric gases retard the flow of radiation out, and that's what gives us the greenhouse effect. All right, well, what gases do that? It's not all the gases in the atmosphere, so we look at the composition of the atmosphere. Most of this you probably know. The atmosphere is about 78% nitrogen, 21% oxygen, to almost 1% argon-40. And that one always puzzles my students, but that's because argon-40 is coming from the decay of potassium-40 in the Earth's crust, which is one of the sources of radiogenic heat. Gives us a lot of argon. None of those gases are greenhouse gases because they don't have electric dipole moments. And the greenhouse gases, the ones that we care about for climate, are much less abundant. Water is the best greenhouse gas in Earth's atmosphere. It has a variable concentration. CO2 is a pretty good greenhouse gas. In fact, its greenhouse effect is often underestimated compared to some of these other ones, and I'll talk a little bit about that. There's about 390 parts per million of CO2 in the atmosphere today, and of course it's going up, and that's what I'm going through this first part quickly so that we can get to the interesting part about global warming at the end. And then there's non-negligible concentrations of methane and nitrous oxide, which are also biogenic greenhouse gases that affect the climate to a lesser extent. Why do these greenhouse gases, why are they greenhouse gases? It's because they have electric dipole moments, and they can be either permanent dipole moments like the water molecule shown here, which is well known to have the bent structure, and so it's got a very strong permanent dipole moment. CO2 is a linear molecule, actually, and so it doesn't have a permanent dipole moment, but it bends, and so it gets an induced dipole moment when it either bends or vibrates. And so CO2, like water vapor, can absorb and re-emit infrared radiation. The way that this happens that's important in the infrared is both by rotation and by vibration. So for water and CO2, vibration-rotation bands are both important. And for water, there's the pure rotation band that's also important. CO2 has pure rotation bands too, but those frequencies are out, those wavelengths are out far beyond the infrared, and so that's not important for climate. There's really three bands that are the most important for the Earth's climate. For water, there's a 6.3 micron vibration rotation band, and there's this pure rotation band. And then for CO2, there's the 15 micron bending mode, the vibration band. I had a chemistry professor once back at University of Michigan, Don Stedman, who demonstrated the bending modes of the CO2 molecule. So he said, consider, CO2 has the oxygens on the end and the carbon atom in the middle. So if my head is the carbon atom and my fists are the oxygen atoms, the bending mode is just that. And that's the strongest vibration of CO2. That's the one that's the most interesting for climate. There's also the asymmetric stretch mode, which is down at shorter wavelengths and doesn't do too much. And then there's the symmetric stretch like this. But the symmetric stretch doesn't have absorption bands because you don't get a dipole moment. You never get out of symmetry when you do that motion. So that band does not appear as permitted transitions in the Earth's atmosphere. Now we'll start to transition out of the introductory slides here, and you can measure these absorption bands by satellites. So we have, for the last 30 or 35 years, we've had Earth orbiting satellites up there. There was one called Nimbus 7, I think, back in the 70s that took this spectrum of the Earth. It was flying down, it had a infrared spectrometer on it, was looking down at the Sahara Desert at this particular time. And here's the scale in wave numbers, which is what the spectroscopists like to use, but there's a wavelength scale in microns down here. This curve right here is the measured flux from the satellite, and then there are black body curves going from 300K down to 175K at the bottom. So what you see is, to first approximation, a black body, but the Earth is not a very good black body at all, much less so than the Sun. The biggest feature in the Earth spectrum is right here. That is the 15 micron CO2 band. That's this bending mode of the CO2 molecule. And that's the one that, as we increase the CO2 concentration of the atmosphere, CO2 is relatively, low in concentration in the Earth's atmosphere. So it's really just this strongest absorption band that is doing most of the warming. So we're increasing not so much the depth of that band, but the width of that band. And that's why CO2 contributes to global warming. out here, let's see, at long wavelengths, this spectrum doesn't go very long, but that's the pure rotation band of water out there, which you see just part of. That's important for climate. There's this 6.3 micron rotation vibration band that's down on the shorter wavelengths. That's modestly important for climate, but actually the Earth's emitted radiation is starting to fall off pretty rapidly there at the shorter wavelengths, so that has less effect than the long wavelength bands. The other feature that you see very prominently when you're looking down from space is this ozone 9.6 micron band. That ozone is a triatomic molecule. That's the bending mode of the ozone molecule there. And so it's sitting right in the middle of the infrared. You would think that would make ozone a very good greenhouse gas, but in fact the greenhouse effect of ozone is pretty small because most of that ozone is up in the stratosphere. And when you're looking down at the Earth, you can see it very well, but it has less of an effect on climate because of the fact that it's concentrated up high. It's very important, though, for this crowd because, you know, we're very interested, some of us, in looking for extrasolar planets out there and getting spectra of their atmospheres. We'll probably do it in the visible first, but Elaine Leger is here, and Elaine led the Darwin study. And of course, Darwin, if it had flown, or it will fly someday, some version of Darwin, that will get spectra of, infrared spectra of extrasolar planets. And one of the prominent features that you would look for there is that ozone band. Very easy to see, even at low oxygen concentrations, as Elaine has argued in his papers. Now here's another way of looking at the absorption features. This slide is given to me by Abe Lehrman at Northwestern. So in this case, he's looking at the absorbance of these different gases. Just if you looked up through the atmosphere, what fraction of the radiation would be taken out by the various gases. And he has water, CO2, methane, and nitrous oxide on it. Water is pretty good across most of the spectrum. That's why it's such an effective greenhouse gas. Although there is a window region here. It's between about 8 and 12 microns. It's called the window region because neither water nor CO2 absorbs very strongly there. If you go up to high CO2 concentrations, there are some hot bands that are in the window region, but at Earth-like CO2 concentrations, that's pretty empty, not much water absorption. And so notice that methane and nitrous oxide both have strong absorption bands that are just sort of at the edge of that window region. Well, that means that's why gases like methane and nitrous oxide are pretty strong greenhouse gases in the Earth's atmosphere today because they absorb where water and CO2 don't. And in fact, you'll often, I don't know, does anybody here read the IPCC climate reports? It's not really the audience that does, but in the IPCC reports, you'll often see this quote that methane is 21 times as strong a greenhouse gas as CO2. And that's true for the Earth's atmosphere today. The IPCC does their homework. They study these things very carefully. But that's because CO2 is 390 parts per million and methane is 1.7 parts per million. And methane is absorbing where the CO2 doesn't. But if you put equal amounts of methane and CO2 in an atmosphere, CO2 is actually the better greenhouse gas. You can see that because here's the 15 micron band of CO2, which doesn't look quite as impressive in this scale, but it's right near the Wien peak for the Earth. And so it has a lot of effect. And the methane band is off at 7.7 microns, which is well short of the Wien peak of the Earth. So that, you know, CO2 is actually the better greenhouse gas than methane, except in the unusual case of the Earth's atmosphere where they're not in the same concentrations. And so that's just something that, you know, it's a sort of a subtlety, but climate, it's not just one gas or the other. You have to think about how all these gases interact in order to figure out their effect on climate. All right, well, those were all low-resolution spectra. If you've looked at high-resolution spectra, you know that the true situation is very complicated because these vibration rotation bands for water and CO2 and the other gases are extremely complex. There are hundreds of thousands of lines across the thermal infrared spectrum. And you know, there's been a lot of work that has gone into understanding the detailed spectra. It was actually all started in the US, at least, for military reasons. The Air Force was interested in heat-seeking missiles, and so they needed to know whether they could see through the atmosphere at infrared wavelengths. And so there's a laboratory called the Air Force Cambridge Geophysical Labs, AFGL, which started all this research on absorption spectra way back in probably in the 60s or so. And that has come to fruition. We used to call these things the AFGL tapes because all the parameters, it's very complicated. You have to have laboratory measurements of this and quantum mechanical calculations so you can figure out which lines are which. And so there's many man-years of effort has gone into that. Now the reason that I mention it is for climate models, you can't afford to do the detailed line-by-line spectra because you have to do these calculations many times, and especially for the 3D models, you've got a whole grid of the Earth and you have to calculate the greenhouse effect at each point on the Earth very many times. And so the tricky thing is to try to do the radiative transfer through these gases accurately but without doing line-by-line calculations. And that, you know, people have worked on that very hard for the present Earth's atmosphere, but as soon as you start getting away from the present Earth, you have to redo all that work. And so there's still, climate is not a solved problem. You still have to work very hard to do this efficiently in a climate model. Now, even if you work very hard, you still don't get the right answer. And why is that? It's because the atmosphere is filled not just with gases that have these absorption spectra that we can calculate and measure, but it's filled with clouds too. And you know, you can look out your window. Today the cloud cover is pretty uniform, so you could probably model that, but oftentimes the clouds are spotty and they're at different altitudes. The high clouds actually warm the climate because clouds have, they not only reflect sunlight, but they have a greenhouse effect because they're made of water vapor. And so the high clouds are cold and they let a lot of the sunlight through, but they have a big greenhouse effect because they're cold. And they re-radiate radiation at low temperatures. And the low clouds, by contrast, reflect a lot of sunlight because they're thicker, but they have a small greenhouse effect because they're warmer. They're closer to the surface. So the high clouds warm and the low clouds cool. And the question is, as the climate changes, how does the relative abundance of high cloud change compared to low clouds? And it's difficult. And you can try to do it in 3D models, but it's almost impossible to do it in simpler models. All right, well, if you put these gases into the atmosphere, they give us a vertical temperature profile, which looks crudely like this. The Earth is warm at the surface, and then temperature decreases very rapidly through the troposphere, which is the convective part of the atmosphere. Almost all the water vapor, as you, I'm sure, are aware, is down at the bottom. That's why we build telescopes up high so that we don't have to look through that. The stratosphere is the region where the temperature warms. These temperature regions are defined by the inflection points on the curve, where the temperature gradient changes sign. So the stratosphere goes up to about 50 kilometers. It's warmed by ozone, which is absorbing the UV radiation from the sun, and that's why the stratosphere warms. Then in the mesosphere, you start to run out of ozone, and the temperature decreases again to the mesopause up at about 90 kilometers, and then it gets very hot up in the thermosphere, and that's because you've got a lot of oxygen up there, and the oxygen is absorbing short wavelength radiation. So that's not important for climate, but we'll come back to that. I've actually got 2 lectures in this series now on hydrogen escape, because it's very important for figuring out how planetary atmospheres evolve, and this question that I'll come back to of how much oxygen would there be in an atmosphere if you didn't have photosynthesis. Question very relevant for remote life detection at some point in the future when we do TPF. Now, I'll show you a few climate model calculations as we go along. There's different levels of climate models, and the ones that are used by the IPCC, people studying global warming, are these big, complicated, three-dimensional general circulation models, which, that's really the state of the art for climate today. But they're time-consuming to run, and as I already said, we can't do them in general for planets that are not like the Earth. So most of what I've done during my career, and what's still the state of the art for doing planetary climates and the habitable zone around stars, are these one-dimensional climate models, which we call radiative-convective models. And they're very simple in principle. The atmosphere is in radiative equilibrium up high, so the stratosphere is in radiative equilibrium, meaning that the flux divergences, the net solar flux divergence plus the net infrared flux divergence has to be equal to 0. But if you get down near the surface in the troposphere, that's where all the water vapor is concentrated. So you would actually get a very big greenhouse effect near the surface, meaning that the radiative temperature profile would get warm very quickly. And of course, that then becomes unstable to convection if you get too steep of a temperature gradient. So what we do, there's different ways to do this in a model, but we use what's called a convective adjustment. If the radiative lapse rate, dt dz, exceeds the critical lapse rate for convection, then you get convection. And the critical lapse rate for convection, we always use what's called a moist adiabat. So an adiabat would be something, if you have an air parcel near the surface and you raise it in the atmosphere, it would cool by expansion or equivalently because you're doing work against gravity. A moist adiabat, and that, the adiabat means you're not exchanging energy with the environment. So this would be an isolated air parcel that you raised up. A moist adiabat is the same thing, except that it's got water vapor in it, and as the air parcel rises, it cools and the water condenses out, and you get the latent heat of condensation that comes out. So the adiabatic lapse rate, the moist adiabatic lapse rate, is not as steep as the dry adiabatic lapse rate. So it's, it's actually very simple atmospheric physics, but you put that together. This is the simplest way of really doing the greenhouse effect and getting things approximately right. You work very hard on the radiation. I typically ignore the clouds. We just sort of cancel those out by painting them on the ground. We use a high surface albedo. But then we work, we put in these convective adjustments. You would not get the right answer without doing that. Okay, well, this brings me to the last part of the talk, and actually the part that's fun to talk about. Lots of people, there are thousands of scientists studying the greenhouse effect today. It's all because we're increasing it. Most of you have probably seen this curve. It's the Keeling curve, measurements of CO2 on Mauna Loa. And of course, we've been measuring since 1958. CO2 was at 315 parts per million. This slide is a couple years old, so it was about 388 parts per million 3 years ago. It's up above 390 parts per million today. The wiggle in the curve, the red curve, it's monthly data at Mauna Loa, and that wiggle, 5 or 6 ppms, that's the breathing of northern hemisphere forests. So the forests take in CO2 because they're doing an excess of photosynthesis during the summer, and in the winter, both plants and animals respire. It's not just the animals, right? So it's mostly the forests doing the action, but the forests are respiring in the winter in the northern hemisphere, and so CO2 goes up in the atmosphere. That leads to global warming, and this is where things start to become controversial, although the temperature curve for the last 150 years is pretty well known. Here's one estimate of the temperature variation since 1860. It's expressed as an anomaly from the 1961 to 1990 mean, so that's 0 in the middle. And you can see that temperatures back in the late 1800s were about a ½ degree Celsius below the mean. For the last 40 years now, they've been going up steeply. And so we're up at about 0.8 degree Celsius above the mean. Nobody none of the serious climate scientists question this because, you know, all the known trends have been taken out of this. Cities, if you have thermometers in cities, then you get the urban heat island effect because there's a lot of pavement and the local albedo is lower. That's all been subtracted from these data. And so the data have gotten better over the last, you know, several decades, so that this trend today is almost certainly real. There used to be a lot of controversy about this. This is an apparent slight dip between 1940 and 1970. That's now generally attributed to sulfate aerosols. When you burn coal, you're putting a lot of CO2 into the atmosphere, which makes the temperature go up, but you're also putting a lot of SO2 in, and that SO2, sulfur dioxide, gets oxidized to sulfate, which gives you little aerosol particles that increase the Earth's albedo. And so for a while there, for maybe 30 years, this is dominated in the northern hemisphere. The northern hemisphere temperatures were actually decreasing slightly. But now we've cleaned up the environment in the US, and I think in Europe all the SO2 has to be scrubbed out of the coal-fired plants. So that's cleaned up to solve the problem of acid rain, or at least address the problem of acid rain, but it makes the greenhouse effect worse. And you know, even if you put those sulfate aerosols back, it doesn't solve the problem. Unless you put them up in the stratosphere. That's one of the proposed geoengineering solutions for climate, is to actually inject SO2 into the stratosphere and try to make a man-made shield. There's just about done here. There's evidence that the surface temperature is increasing more rapidly recently. This is out of the 2007 IPCC report. Remember, the IPCC is the Intergovernmental Panel on Climate Change. And this is a group, you know, of scientists from all over the world. There's, I think, 3,000 people in the IPCC. They all shared the Nobel Prize with Al Gore a few years ago for this research. They're really very good. And here they've drawn trend lines for the last 150 years. And then this blue line is the last 100, I think. And then the last 50 and the last 25. And you can see that the slope of that curve is increasing, so things are getting warmer now than in the past. And then finally, I'll show you one last slide because it's kind of fun. There are skeptics out there who keep arguing that, you know, this is not happening. Where do they get their arguments? Well, here's the last 15 years of average temperature data going from 1996 to 2010. It's two different sets of measurements. I've actually forgotten what so the black is all meteorological stations, and then the red is some index of that from another set of data. They agree pretty much. But if you notice, if you go back to 1998, there was a real high point there. So for reasons that are not entirely clear, 1998 was a really warm year. And then if you start your measurements back in 1998, the skeptics will say, well, look, the climate hasn't warmed that much since that year. And, you know, but we just saw that the climate's been warming drastically for the last 40 years. So really scientifically, there isn't that much debate. So let me just leave you then with two conclusions. One is that the greenhouse effect can be accurately calculated using either one-dimensional or three-dimensional models. And so the physics of the IR absorption by CO2 and water and the other greenhouse gases is very well understood by this point, but it remains tricky to parameterize that in climate models, to make it go fast enough to actually do the calculations. And then finally, in spite of the fact that you can do that physics very well, we can't really predict climate very well because we don't know what the clouds are going to do. And that's almost impossible in 1D models and still very tricky in 3D models. So that's really all I wanted to say this morning, and I'm happy to answer some questions. Yes?
Can you make a few more comments on the aerosols? I think in the models, you just have the greenhouse gases, you overshoot the temperature by a lot unless you put in the aerosols, correct?
Yeah, so the IPCC has worked very hard to try to show that the climate models can reproduce that temperature effect. And that's why we think we know that the sulfate aerosols cooled, because when they put that in the models, they could reproduce that shape of that curve. And when you neglect that, you just get monotonic warming. If you go back further in time, there are volcanoes that go off every now and then, and some of them are very sulfur rich, so they put a lot of SO2 into the stratosphere, and for about half a year to a year, you'll get a sulfate aerosol layer up there that temporarily increases the Earth's albedo and causes global average temperatures to decrease by about 0.5 degrees Celsius. But then it pops right up a year or two later, because those sulfate aerosols get down into the troposphere where it's raining, and SO2 or sulfate is quickly taken up by water. It's very hygroscopic, and so it rains out, and the effect of the aerosols goes away. Yes, Elaine.
Concerning the idea of climate engineering, how much SO2, what is the weight, the mass of SO2 you would need to introduce to the stratosphere?
Well, I'm not sure I know the numbers off the top of my head, but we could, you can imagine building big guns on the surface. I mean, this has been proposed, and you shoot this stuff up continually all over the globe. And if you keep doing that, you can counter the effects of, say, one CO2 doubling. At a cost that's actually cheaper than any of the other proposed geoengineering solutions. So this is one that has gotten a lot of attention. Most of the meteorologists don't like this. So one of the initial objections to that was people were worried as whether that would affect the ozone layer. Because there's the ozone hole down in Antarctica that's caused not by sulfate aerosols, but you get these nitrate aerosols that form in the cold polar stratosphere, and then you get heterogeneous chemistry that occurs, chlorine chemistry that occurs on those particles and destroys the ozone. Well, so the immediate question was, would you get that same type of heterogeneous chemistry if you did this geoengineering in the modern stratosphere? Paul Crutzen actually wrote a paper. I don't know if people know Paul here. He's at Germany at a Max Planck Institute. He's a Nobel Prize winner. He got the Nobel Prize in chemistry. He shared it for initial work on the ozone problem back in the 1970s. No less a person than Paul Crutzen actually wrote a paper showing that it's probably safe from an ozone standpoint to do this, because chlorine levels are low enough now that we're controlling it, that you would not get massive ozone destruction elsewhere in the world. So it's something to consider, but a lot of us don't like it, because suppose you have some event that keeps you from shooting these big guns off. Maybe we have some kind of world turmoil, and all of a sudden we lose the capability of doing this. Well, then CO2 has built up much higher, and if you quit counteracting it, then the climate adjusts very quickly. And one of the bad things about climate change is just the rate at which it happens, and that would make that problem even worse. So I don't think it's a very good idea. Yes?
You mentioned that you can take all these 10,000 molecular absorption lines in detail into account in the three-dimensional GCM models. Do you know how they do that in the radiation transfer?
Yeah, you can do it. It just takes work. And so the method that has been used the most is what's called the correlated K method. And what you do here is you have broadband spectral intervals. And in a GCM, it might be just 16 spectral intervals across the thermal infrared. And then you go in there and you use the HITRAN database. HITRAN is this database that was started from the AFGL tapes. And that's what a lot of people still use. And you go in there and measure the line-by-line, or you use a line-by-line program to calculate the transmission. And then you bin the coefficients by strength, and you divide them into different intervals there, and get a K. I should show you the math, but you just parameterize the transmission as the sum of exponentials, so it looks like Beer's law. And that's quick enough then to handle this, but you still get problems because you've got both water and CO2, so if you did those independently, then you have to convolve the K coefficients, which is slow, so you have to derive these for water-CO2 mixtures, and then if you put in another greenhouse gas, you have to either worry about whether to convolve it or do lots of calculations ahead of time to set up big lookup tables, so it's tedious. Yes, one more maybe, and then we'll go to...
Say more about clouds. Is the difficulty of forming and destroying them from a theoretical standpoint? Why is it so hard to understand clouds?
Well, the clouds are hard to understand, not because we don't understand the microphysics. That's been well studied, but they tend to be sub-grid scale on a GCM grid, so that you have to parameterize their effects. And that, that's really the problem with meteorology is it's fluid dynamics, and fluids have scales of energy and also physical processes that are happening on scales from very large global scale right down to, you look out on a typical day and you'll see clouds that are only a kilometer across or so. And a typical GCM three-dimensional grid square is maybe 200 kilometers on a side. So you have to then parameterize it, and we can do that for the present climate because there's lots of observations, but how do you do that for other climates? It's difficult to make a parameterization that people will think is reliable. And that's why one thing that I missed on the slide, when you just double CO2 from the radiative effect alone, you get 1.2 degrees Celsius. You put in the water vapor feedback, I'll talk about feedbacks next time, and you get 2.5 degrees Celsius. But you look at the range of IPCC models, and it's anywhere between 2 and 5 degrees Celsius per CO2 doubling. And the range of uncertainty is almost entirely due to the different parameterizations of clouds in the model. And so that's why they don't agree with each other.